Greetings all. I hope you're enjoying your day of distance learning, but that you'll take some time to get outside and enjoy God's creation and get some fresh air and some sunshine. Most of what I'd like to do right now is to go over some of the example problems in the book and give you some ideas and suggestions about patterns and things to do to help solve these kinds of problems. So let's look at problem in section 17.8. And it says we've got a 10th molar aqueous solution of lactic acid. Now we already went over this in class, but this is a review to set the stage for the rest of the problems. What do we notice in this problem? Well, we have a 10th molar solution. The next thing we look at is lactic acid, which right off the bat we say it must be a weak acid because it's not one of the strong acids I had to measure. You also notice we know its pH. That means that we can find the hydronium ion concentration, and if necessary, we would be able to find the hydroxide ion concentration from that. And then finally, our goal is to find the Ka. One other piece of information that you might not have noticed is that lactic acid is the hydrogen ion connected to the lactate anion. And so whatever the molarity of the hydronium ions is also going to be the molarity of the lactate ion. Because for every lactic acid molecule that splits up, you get one lactate and one hydrogen ion, 1-to-1 ratio. So you actually know 4 different things. You know the pH because it's given, but you also know hydronium molarity, hydroxide molarity, and the lactate ion molarity. Keep that in mind as we go through this problem. Now, the strategy, as always, is to, first of all, you want to write your equation. What is the equation? There's the equation that's happening. Your lactic acid is being put into water. Your lactic acid being added to water, and it's dissociating into the lactate ion and the hydronium ion. The next thing you want to do is to write your equilibrium expression. They mention it right here, and here is your expression right there. Equilibrium expression. The third thing that you need to do is to figure out a way to find some numbers to plug into the expression. And that's where the ice chart comes in. Then the last thing you do, which is over on the next page, is to actually plug the numbers in. So I keep reminding students over and over, break it up into 4 parts. Part 1, part 2, automatic. Don't even do anything else. A lot of times doing part 1 and part 2 jogs the memory so you can do part 3. And then once you have part 3, there's the numbers that are going to go into your equilibrium expression, the molarities at equilibrium. So in order to find the hydronium ion molarity, that's 10 to the negative 2.43, which gives us, there's my molarity. That's the value of X in the ice chart. That represents how many of your lactic acid molecules are going to split up. If you start with this many, and 3.7 times 10 to the minus third, which is X, break up, then you have 0.10 minus X left over at equilibrium. It's like saying if you have X squared ants couples, right there, you're going to get X guys and X girls that split up. And over here are the rest of the squared ants couples that did not split up. Then we take our values, and this is the plug part. You plug them in to your equilibrium expression. Now, when we look at the denominator here, we ask ourselves, is this number going to affect anything when I subtract it from 0.10? And in this case, the answer is yes. When you only are working with two significant digits, these two numbers, that one and that one, are close enough that when you subtract, it probably makes a difference. So you can't simplify it by ignoring the 0.0037. Here's another clue. If you look at the k value that you eventually calculate, and if you multiply it by a factor of 100, you get 1.4 times 10 to the minus 2. And that's really, really close to your original concentration, which is 1 times 10 to the minus 1. Another reason for taking it into consideration when you subtract. All right. Now, is there a rule of thumb about when to keep in mind the number of molecules that split up, the number of weak acid or weak base, or weakly soluble particles that split up, and when you can ignore the number that's split up? And first of all, in general, if confronted by Al-Qaeda, I would guess it'll be able to be ignored, because most weak acids and weak bases and weakly soluble salts don't split up appreciably. There are a few that do. But if you need proof, there it is. Multiply your Ka or your Kb by 100. And if that number is still less than the molarity of your original weak acid or weak base, then you've got to keep it in the equation. You can't ignore it. All right, next question. What is the pH of an aqueous solution of a weak acid or a weak base? Well, we actually just did a problem like that, but they're all a little bit different. So let's take a look at this one. It says calculate the pH of a 0.020 molar solution of benzoic acid, given that the Ka is 10 to the minus fifth. So what do we see? We've got my original molarity, and it's not like a 0.000 anything. It's relatively hefty for a concentration. We have benzoic acid, which we know is a weak acid. And then we got 10 to the minus fifth here. 10 to the minus fifth tells me that this is a lot smaller than the Ka in the previous problem. So there's a good chance I can ignore the minus x part. So I'll keep that in the back of my mind. Now, we're going to write, first of all, write the equation. Here is your benzoic acid. You put it in water. Water yanks it apart. You get the hydronium, and you get the benzoate ion. Again, keep in mind that you could also ignore the water if you just wanted to call this H+. It's not going to affect anything. Number 2 is way down here. The next thing I do automatically is write the Ka expression. This is the expression, products over reactants. Part 3, come up with a way to find numbers to put into the equation. I'm starting off with this molarity, and X of those molecules are going to split up. So when I'm done, I have 0.020 minus X that have split. Or we could say if I had 0.020 square dance couples and X square dance couples split up, I'd get X guys and X girls. So there's my values at equilibrium. So I plug them into the expression down here. Here's the plug part where you plug it in. And now you got to chug through the math. Plug and chug. And we ask ourselves the question, can I ignore the minus x? Because it makes life simpler. So I take my Ka, which is 10 to the minus fifth, multiplied by 100, I get 10 to the minus third, 0.001. And that number, whoops, I don't know what just happened there. That number, 0.001, is still smaller than the original concentration of 0.02 molar. It's smaller by a factor of maybe 20. So it's close, but the 2 sig digs, I can probably ignore it. Now, once I solve for my value of x, x is the molarity. X is the molarity of my hydroniums. It's also the molarity of my anions and the benzoate anion. But if it's the molarity of my hydronium ions, then it's an easy thing then to take the negative log of that in order to get the pH. And if I needed to, I could also find the pOH by subtracting that number from 14. All right, let's take a look at this problem right here. What is the pH of a 0.0010 molar solution of formic acid? Talked about this a little bit later. 1 carbon as opposed to the ethanoic or acetic acid, which has 2 carbons. There's my Ka. And so to speed things up, equation, part 1, equilibrium expression, part 2. The plug part is my ice chart. Ice for initial change equilibrium. Plug it in. Can I make my approximation? So I multiply the Ka by 100, and I get 1.8 times 10 to the minus 2. My original molarity is smaller than that, actually. 1 times 10 to the minus 3. So sorry, folks, you're going to have to keep it in there. And if you're going to keep it in there, that means you're probably going to get stuck with a quadratic equation. And once you solve for that, and good luck with that, we get our molarity, and then from the molarity we can find our pH. All right, let's look at this next problem. Now this time, instead of having a weak acid or a weak base, we're going to have a basic salt. What do we mean by a basic salt? We haven't used that term yet. And by a salt, you know that a salt is going to be a cation and an anion. You know a salt is the product, it can be at least, you can make a salt by combining an acid and a base, because acid plus base produces a salt plus water. And this is a basic salt because you would recognize that sodium theoretically could come from the strong base, sodium hydroxide. And acetate could come from the weak acid, acetic acid. So if you have a strong base plus a weak acid, you expect the pH to be greater than 7. And that's a good thing to keep in mind. pH greater than 7. So that when you solve this problem, if your pH is not greater than 7, your answer doesn't make sense and you probably made a mistake. So, what's our strategy? The Shaw strategy is, first of all, write the equation. Now, the equation, you'll notice, is not this. Acid plus base is salt and water. The active equation is the equation that actually affects the pH. And the equation that actually affects the pH is that this salt, remember, is made out of two ions, sodium and acetate. So sodium and acetate and water molecules are going to be colliding with each other. If we're playing the game, what's in the beaker? We got three particles in here. We got sodium particles, we've got water molecules, and my pen writes too thickly to make this nice, and we also have acetate in there, AC for acetate. Three things in there, and they're all colliding with each other. Only one collision is effective. Only one collision does anything. If acetate ions collide with sodium, water just yanks it apart because it's soluble. If sodium collides with water, you could make sodium hydroxide, but water will just yank it apart because it's a strong base. But your acetate will combine with the water. This is the effective collision, so this is the equation that matters. Your acetate ion collides with water to make acetic acid and hydroxide. Why is it going to the right? Because you're making a molecule with a strong bond, a weak acid. Now, before I go on solving the problem, here's an important point. Is the solution going to be acidic or basic? We already said it's going to be basic because you have a strong base winning out over a weak acid. But, just so you see, this weak acid has nothing to do with the pH. It's hydronium ions that affect the pH. The molecule doesn't affect the pH at all. The hydroxides affect the pH, which is why your solution will have a pH greater than 7. So once we have our operational equation, then we want our expression. Number 1, number 2, number 3, we want to find our data to do the plug part. And it looks very, very familiar to what we've had before. The reaction has to go to the right because you have 0. Any place you have 0, that's the direction the reaction has to go. So it's going to go to the right. So you're going to have a positive X and a positive X and a minus X. And now we plug it in down here. There's my plug part. And when we get ready to solve the problem, we can multiply both sides by the denominator. And that gives me this expression. Take the square root of both sides. And now I have my molarity. This is the molarity of my that and that. It's the molarity of my weak acid, and it's also the molarity of my hydroxides. Since it's the molarity of my hydroxides, I can find the pH by taking the negative log of it and subtracting it from 14. Or, the other way we can do it is to remember that hydronium times hydroxide equals 10 to the minus 14th. And that way we can find the hydronium ion molarity and take the negative log of that, and we get 8.46. Now, some students make the mistake, they take the negative log of this. Well, because you're taking the negative log of a hydroxide, you're going to get the POH when you take the negative log of the hydroxide, and the problem wants the pH. So be careful you don't make that mistake. Let's look at this example. What is the pH of the solution that results from mixing 25 mils of 0.016 molar ammonia and 25 mils of 0.016 molar hydrochloric? Now you'll notice, and it's not a coincidence, that they're obviously talking about a neutralization point where your moles of base equal your moles of acid. Because 25 times 0.016 is going to equal 25 times 0.016. Because your volume times your molarity of your acid equals the volume times the molarity of your base. And that's true at the neutralization point when the acid has neutralized the base. You might remember this formula. Now, you might think, oh, well, neutralization, that means my pH is going to equal 7. And you would be wrong, because you'll notice that even though hydrochloric is a strong acid, ammonia is a weak base. So this is not going to be true. And in fact, if we think about it, my pH is going to be greater than 7, less than 7, because of the fact we have a strong acid that's going to win out over the weak base. So the question becomes, so what's going to make the pH less than 7? I see why that's got to be the case from the logic, but what actually makes the pH less than 7? And that is because every time you have a weak acid or a weak base, you've got to think of its conjugate. Your equation is always going to be the equation of the hydrolysis of the conjugate of the weak acid or the conjugate of the weak base. Your equation is always going to be the hydrolysis of the conjugate. And by hydrolysis, we mean water. Okay? So, step 1, write the balanced equation. Step 2, you're going to need to write your equilibrium expression. So here's my balanced equation. The balanced equation is not that one. This is the weak base. This is the net ionic of the strong acid. Notice the spectator ion isn't there. And here's my conjugate. This is the conjugate of the weak base. And that is what sets up my equation. Here's the equation. The conjugate of my weak base, hydrolyzed with water. It donates a proton to the water, creating the hydronium ion. And as a result, it ends up being ammonia. My conjugate, my weak acid, becomes my conjugate base in this particular equation. We also know that we have the same number of moles of hydrochloric as ammonia when we multiply volume times molarity. Same number of moles. It's a 1-to-1 ratio. So, we continue on. Here's my equilibrium expression down here. Products over reactants, step 2. Step 3, we need a way to find the numbers to plug in. We're going to use an ice chart. And these ice charts should start looking very, very familiar. Now, all these ice charts have been the same so far, and this is important because it's going to change later in the book. All these ice charts look exactly alike, with minus x, plus x, plus x, because we have one substance in the water. We have a salt in the water. We have a weak acid in the water. We have a weak base in the water. We don't have something else. Later on, we're going to look at buffers when you have two things in the water at the same time. But right now, we only have one thing in the water. The reaction has to go to the right. We plug our numbers in. And again, we have an easy variable to solve for, x. So we take the square root of both sides here. There's my hydronium ion concentration, which incidentally also happens to be the ammonia molarity. But we're interested in the hydronium ion molarity because we can take the negative log of that to get the pH. Now here's an interesting little story, a sidelight. Looks like my page got folded under there in the copy machine. But this is deadly nightshade, and it's kind of interesting because last spring I was walking in our neighborhood, and a neighbor that whose husband had just died, and she was working in the lawn, and we had chatted a number of times. She had a strange plant growing in her back lawn, right by the trail, and asked what it was. And I did a little research, and it actually was nightshade. It was belladonna, and which is not a good thing to have in your lawn, especially if you have pets or children running around that might look at the little berries and think that they can be eaten. Not in this case, because it contains a compound called atropine. My work out in Idaho in the detection of chemical weapons, I've actually worked with the degradative products of sarin gas. Something I'm not supposed to say too much about. But that has already been used and might even be being used today by Hassan in Syria against the Kurds in the northern part of his country, where he's used chemical weapons before. Not a nice thing going on in the country of Syria. Thousands and thousands of people killed by all kinds of different ways. But there was also a sarin gas attack in Japan in the 1990s, and the Gulf War, which is one of the reasons that created the funding for a lot of the research I did in the 90s and the early 2000s in the detection of chemical weapons. But look at all the phrases that come from people that have a little too much atropine. You get very, very red because all your blood vessels dilate, so you're red as a beet. And your eyes dilate as well, so you can't focus. You might as well be blind as a bat. And you get really, really thirsty, so you're dry as a bone. And because of all this blood rushing through your body temperature goes up, hot as a hair. And of course, it can also affect your ability to think. And you become, like in Alice in Wonderland, mad as a hatter. Actually, the phrase mad as a hatter comes from the use of mercury compounds by the people that made felt hats out of beaver skins during the time when Lewis Carroll wrote the book Alice in Wonderland. Anyway, it is one of those kinds of organic bases. See the INE, very similar to caffeine, nicotine, morphine, heroin, amphetamine, all organic bases. All not so nice stuff in various ways. We can tolerate the caffeine without too much problem. Nicotine, highly addictive. Morphine can be used to help people wean them off of worse drugs like heroin. Amphetamine, of course, speed, has all kinds of serious consequences as well. All very addictive. So, moving right along. We've talked about polyprotic acids before, and we talked about how you generate the first proton, and then usually about a factor of 10,000. This seems to be pretty consistent. 10,000 times less that you're going to lose the second proton. We can make a general rule of thumb up here. I would remember this, by the way. When you have a polyprotic acid, your pH is primarily the result of losing the first proton. You can basically stop there. When you try to make any minor adjustments to the pH by trying to lose the second proton, it's not going to make any difference at all. And here you have this amazing drawing over here. Must have been an artist that did this drawing, showing you playing the game of what's in the beaker. And when you, in your beaker will be your spectator ion right there. And then you're going to have different anions right there in the beaker as it dissolves. So we need to have an operational equation. And the operational equation is simply going to be this one right here. The carbonate ion is going to hydrolyze. We can pretty much ignore what happens in the second step because it's a factor of 10,000 times less. And therefore, we'll just focus on that. So you'll notice how we always write that equation right there. Here's step one, we'll write the equation. Well, there's step one. I like to write it across the top. Remember, we don't worry about the water part at all. And now your equation looks exactly like, or I should say your ice chart looks exactly like you've seen it before. Minus x plus x plus x. Here's my equilibrium expression, which is part 2. We're going to plug our numbers in down here. And you can see it's starting to look like a quadratic equation. And in fact, if we take our Ka, multiply it by 100, we get 10 to the minus 2. And we're looking here at 10 to the minus 1. So it might be a little bit too close for comfort. It might not be a bad idea just to go ahead and consider it. Now, in this case, it looks like they're going to not consider it. They're going to do the consider. They're going to go ahead and ignore it. It's close. It's very, very close. But they're going to ignore it in this case. And now they're going to say, what's going to happen if we were to go ahead and lose the second proton? Well, when we go ahead and lose the second proton, here's our equation again for losing the second proton. We're starting off with this from the loss of the first proton. Okay? And notice now my ice chart looks a little bit different. I have this left over from losing the first proton as well. Because remember, in the first equation, higher up, they are in a 1-to-1 ratio. For every one of these, I had one of these. So the second ice chart takes the information from the first ice chart. And again, I have minus, plus, plus, because in this case, the reaction is going to go to the right again, because remember, it has to if you got a 0 there. And now I plug my numbers in, and then you can see my molarity. Solve for the molarity of the carbonic acid. And the hydroxide produced in this reaction is very, very, very small. It's not really that important as far as consideration. So that concludes solving a whole bunch of these problems. And in class, we are going to take a separate look at the molecular structure and how that's related to bonding and acid-base behavior. We're going to take a look at that. So this is sort of going to draw on several different chapters. It'll be a good review as well as teach you something new. And when you read ahead, we're also going to be looking at some interesting questions that are often AP test questions. For example, why are carboxylic acid Bronsted acids? Meaning they donate a proton. That's not too difficult. We've actually talked about it. But this question here, why are anions Bronsted bases? How is it possible for an anion to receive a proton, be a Bronsted base? And why are hydrated metals, metal cations, Bronsted acids? How do they lose protons? And what about acids and bases that fit the Lewis definition? Lewis acids receive a pair of electrons. Lewis bases donated pair of electrons. And we'll consider that later. Ciao for now.